memory and forgetting, how our mind works. Welcome to one of the most fascinating and mysterious aspects of human psychology, memory. Every moment of your life, your brain is performing an incredible feat, capturing experiences, storing them, and retrieving them when needed. Yet memory is far from the perfect recording device we might imagine it to be. It's selective, reconstructive, and surprisingly unreliable in ways that can be both troubling and remarkable. Understanding how memory works isn't just an academic exercise. Your memory shapes your identity, influences your decisions, and determines how you learn and grow. The stories you tell about your past, the skills you've developed, and even your sense of who you are all depend on the complex processes of memory formation, storage, and retrieval. What makes memory so intriguing is that it's not simply a biological hard drive storing exact copies of experiences. Instead, memory is an active, creative process that reconstructs the past each time we remember. This reconstruction can be influenced by our current emotions, beliefs, and knowledge, sometimes creating memories that feel completely real but never actually happened. The study of memory reveals profound truths about human nature. We don't just remember facts and events. We remember meanings, emotions, and personal significance. Our memories are not just records of what happened, but interpretations of what happened, filtered through our unique perspectives and constantly updated by new experiences and understanding. Today, we'll explore 10 crucial aspects of memory and forgetting that reveal how this remarkable system works, why it sometimes fails us, and how we can work with its natural tendencies to improve our learning and recall. First component, short-term memory. Short-term memory is our mind's temporary workspace, holding information for just a few seconds to a few minutes while we actively think about it. Think of it as your mental notepad. It's where you hold a phone number while dialing it, or keep track of the first part of a sentence while listening to the end. The capacity of short-term memory is remarkably limited. George Miller's famous research in the 1950s identified what he called the magical number 7, plus or minus 2. Most people can hold between 5 and 9 pieces of information in short-term memory at any given time. This explains why phone numbers are typically 7 digits long. It's right at the edge of what most people can remember. However, we can dramatically increase our short-term memory capacity through a process called chunking. Instead of trying to remember individual pieces of information, we group them into meaningful units. For example, the number sequence 197620001 is 8 separate digits that would overwhelm short-term memory, but chunked as 1976 to 2001, it becomes just 2 meaningful units that are much easier to remember. Short-term memory isn't just about storage, it's also about manipulation. Working memory, a related concept, refers to our ability to not just hold information temporarily, but to work with it mentally. When you multiply 23 times 47 in your head, you're using working memory to hold intermediate calculations while performing mental operations. The duration of short-term memory is surprisingly brief. Without rehearsal or active attention, information typically fades from short-term memory within 15 to 30 seconds. This is why you might forget someone's name immediately after being introduced if you don't make an effort to repeat it or use it in conversation. Interference plays a major role in short-term memory loss. New information coming in can push out older information, like trying to fit too many items in a small box. This is why it's so difficult to remember a new phone number if someone starts talking to you while you're trying to dial it. The distinction between short-term and long-term memory isn't just academic. It has practical implications for learning and daily life. Information must pass through short-term memory to reach long-term storage. So understanding its limitations helps explain why cramming for exams is less effective than spaced practice. Attention is crucial for short-term memory function. Information that doesn't receive conscious attention never makes it into short-term memory at all. This explains why you might drive home from work without remembering any details about the journey. Your attention was elsewhere, so the information never entered your memory system. Individual differences in short-term memory capacity help explain differences in academic performance, problem-solving ability, and learning speed. People with larger working memory capacity can juggle more information simultaneously, making complex thinking tasks easier for them. Modern life places enormous demands on our short-term memory systems. Multitasking, constant interruptions, and information overload can overwhelm these limited capacity systems, leading to forgetfulness and reduced performance. Understanding these limitations can help us design better strategies for managing information and attention. Second component, long-term memory. Long-term memory is your brain's vast storage system, capable of holding virtually unlimited amounts of information for periods ranging from minutes to an entire lifetime. Unlike short-term memory's temporary workspace, long-term memory serves as your permanent library of knowledge, experiences, and skills. Long-term memory isn't a single system, but rather consists of multiple interconnected systems. Explicit memory, also called declarative memory, includes information you can consciously recall and describe. This divides further into episodic memory for personal experiences and semantic memory for general knowledge and facts. Episodic memory stores your personal experiences, your first day of school, last week's vacation, what you had for breakfast this morning. These memories include not just the facts of what happened, but also the context, emotions, and sensory details that make each experience unique and personally meaningful. Semantic memory contains your general knowledge about the world. Knowing that Paris is the capital of France, that dogs are animals, or that 2 + 2 is equal to 4. This knowledge feels timeless and objective, without the personal context that characterizes episodic memories. Implicit memory, also called procedural memory, includes skills and habits that you can perform without conscious thought. Riding a bicycle, typing on a keyboard, or driving a familiar route all rely on implicit memory. These memories are expressed through behavior rather than conscious recall. The process of forming long-term memories involves encoding, storage, and retrieval. Encoding transforms experience into a format that can be stored in the brain. Storage maintains information over time, while retrieval brings stored information back into consciousness when needed. Long-term memory formation is not passive but requires active processing. Simply being exposed to information doesn't guarantee it will be remembered. Meaningful processing, emotional significance, and repetition all improve the likelihood that information will successfully transfer from short-term to long-term memory. The organization of long-term memory is associative rather than alphabetical. Related concepts, experiences, and memories are linked together in networks of association. This is why remembering one thing often triggers memories of related experiences or information. Forgetting from long-term memory can occur through several mechanisms. Decay theory suggests that unused memories gradually fade over time. Interference theory proposes that new learning can disrupt older memories, while retrieval failure suggests that memories remain intact but become inaccessible. The relationship between short-term and long-term memory is bidirectional. Not only does information flow from short-term to long-term storage, but long-term memory also influences what we pay attention to and how we interpret new experiences. Your existing knowledge shapes what you notice and remember about new situations. Third component, Ebbinghaus forgetting curves. Hermann Ebbinghaus, a German psychologist in the late 1800s, conducted the first systematic scientific study of memory and forgetting, using himself as the sole subject. He memorized lists of nonsense syllables and then tested how much he could recall after various time intervals. His findings revealed fundamental patterns about how we forget. The forgetting curve shows that memory loss is not linear, but follows a predictable exponential pattern. The most dramatic forgetting occurs immediately after learning, with about 50% of new information forgotten within the first hour. After that, the rate of forgetting gradually slows down, but continues steadily over time. Ebbinghaus discovered that without rehearsal or review, people forget approximately 40% of new information within 20 minutes, 60% within an hour, and 70% within 24 hours. These findings were revolutionary because they demonstrated that forgetting follows mathematical laws rather than being random or unpredictable. However, the forgetting curve varies significantly depending on several factors. Meaningful information is forgotten much more slowly than meaningless information like Ebbinghaus's nonsense syllables. Personal experiences, emotional content, and information that connects to existing knowledge all show much better retention over time. The spacing effect, also discovered by Ebbinghaus, shows that distributed practice is more effective than mass practice for long-term retention. Studying something for 1 hour each day for 5 days produces better long-term memory than studying for 5 hours in a single session, even though the total time investment is identical. Modern research has confirmed and extended Ebbinghaus's findings across different types of material, age groups, and learning contexts. The basic pattern of rapid initial forgetting followed by a more gradual decline appears to be a universal feature of human memory. Understanding forgetting curves has practical implications for education and training. The key insight is that review must be timed strategically to combat natural forgetting patterns. The most efficient review schedule involves increasing intervals between practice sessions, reviewing after 1 day, then 3 days, then a week, then 2 weeks, and so on. Spaced repetition systems, now widely used in language learning apps and educational software, are based directly on Ebbinghaus's discoveries. These systems use algorithms to schedule review sessions just before you're likely to forget information, maximizing retention while minimizing study time. The forgetting curve also explains why cramming for exams, while it might help short-term performance, produces poor long-term retention. Information learned through cramming follows the steep forgetting curve, with most details disappearing within days or weeks after the exam. Emotional significance can dramatically alter the forgetting curve. Traumatic or highly emotional memories may show little forgetting over time, while neutral information follows the standard exponential decline. This suggests that emotional arousal during learning can override normal forgetting processes. Fourth component, serial position effect. The serial position effect demonstrates that our memory for items in a list depends heavily on where those items appear in the sequence. This phenomenon reveals important insights about how memory systems interact and has significant implications for learning and communication. The effect consists of 2 components, the primacy effect and the recency effect. The primacy effect shows that we remember items at the beginning of a list better than those in the middle. The recency effect shows that we also remember items at the end of a list better than those in the middle. Items in the middle of the list suffer from poor recall compared to those at either end. The primacy effect occurs because items presented first receive more attention and rehearsal. When you hear the first few items in a list, your short-term memory isn't yet full, so these items can be processed more thoroughly and have a better chance of transferring to long-term memory. The recency effect happens because the last few items are still present in short-term memory when recall begins. These items haven't had time to fade from the temporary storage system, making them readily available for immediate recall. However, if there's a delay between learning and recall, the recency effect disappears while the primacy effect remains. This suggests that recency depends on short-term memory, while primacy reflects successful transfer to long-term memory. The serial position effect has been demonstrated across many different types of material and situations. It applies to word lists, speeches, job interviews, product presentations, and even social impressions. The position of information in a sequence consistently influences how well it's remembered. In educational contexts, the serial position effect suggests that the most important information should be placed at the beginning or end of lessons, presentations, or reading materials. The middle portions are most likely to be forgotten and may need additional reinforcement or repetition. Marketing professionals use serial position effects strategically in advertising and product placement. Television commercials at the beginning and end of commercial breaks are remembered better than those in the middle. Product placement at the beginning and end of store aisles receives more attention than middle placements. The effect also influences social perception and impression formation. In job interviews, candidates who interview first or last are often remembered more clearly than those in the middle. This can create unfair advantages or disadvantages based purely on scheduling order, rather than qualifications. Understanding serial position effects can help you structure communication more effectively. When giving presentations, place your most important points at the beginning to benefit from primacy effects, and end with a strong conclusion to leverage recency effects. Bury less important details in the middle, where they're less likely to be remembered. The phenomenon also explains why breaking long lists or presentations into smaller chunks can improve overall recall. Instead of one long sequence with poor recall for middle items, multiple shorter sequences give more items the advantage of beginning or ending positions. Fifth component: false memories. False memories are recollections of events that never actually occurred, or memories that differ significantly from what actually happened. These aren't deliberate lies or fantasies, but genuine memories that feel completely real to the person experiencing them. The existence of false memories reveals fundamental truths about how memory works. False memories can be surprisingly detailed and emotionally compelling. People might vividly remember being lost in a shopping mall as a child, complete with sensory details about the experience, even when family members confirm that this event never happened. The subjective experience of false memories is indistinguishable from that of true memories. Research by Elizabeth Loftus and others has demonstrated how easily false memories can be implanted. In controlled experiments, researchers have successfully created false memories for events like being lost in a mall, spilling punch at a wedding, or witnessing impossible events. These studies show that memory is more reconstructive than reproductive. The mechanism behind false memory formation involves the same processes that create true memories. When we remember something, we don't simply replay a recording of the original event. Instead, we reconstruct the memory from various pieces of stored information, filling in gaps with logical inferences and expectations. Source monitoring errors contribute to false memory formation. Sometimes we remember information correctly, but forget where we learned it. A story someone told us might be remembered as something we personally experienced. A dream might be recalled as a real event. Movie scenes might be incorporated into personal memories. Suggestion and social influence play major roles in false memory creation. Leading questions, repeated suggestions, and social pressure can all contribute to the formation of false memories. This has important implications for eyewitness testimony, therapeutic practices, and childhood memory recovery. The misinformation effect demonstrates how information encountered after an event can alter memory of the original event. If someone tells you that a car was red when you originally saw it as blue, you might later remember it as red. Post-event information can literally overwrite original memories. Imagination inflation shows that simply imagining events can increase confidence that they actually occurred. The more vividly and frequently we imagine something, the more likely we are to later remember it as a real experience. This explains how therapeutic techniques involving imagination can sometimes create false memories. Individual differences in susceptibility to false memories are significant. Some people are more prone to memory distortions due to factors like absorption, imagery ability, and dissociation tendencies. However, even people with excellent memories can develop false memories under the right conditions. The implications of false memory research extend far beyond psychology. Legal systems, therapeutic practices, and personal relationships are all affected by the reality that memory is not the reliable recording device we often assume it to be. Understanding these limitations is crucial for making informed decisions about memory-based evidence and claims. Sixth component, confabulation. Confabulation is the production of fabricated, distorted, or misinterpreted memories without the conscious aim to deceive. Unlike lying, where someone knowingly tells falsehoods, confabulation involves genuine false memories that the speaker believes to be true. This phenomenon provides crucial insights into how memory reconstruction works. Confabulation often occurs in people with brain injuries, particularly damage to the frontal lobes or memory-related brain structures. However, it also occurs in healthy individuals under certain circumstances, revealing that confabulation represents an extreme version of normal memory processes rather than a completely abnormal phenomenon. There are two main types of confabulation. Spontaneous confabulation involves obviously false or impossible memories that are produced without any prompting. Provoked confabulation occurs in response to questions or cues. When someone fills in memory gaps with plausible but incorrect information. The mechanism behind confabulation involves a breakdown in source monitoring and reality testing. The brain continues to try to make sense of incomplete or fragmented memory traces, filling in gaps with information that seems logical or consistent with the person's beliefs and experiences. Normal memory reconstruction shares many features with confabulation. When we remember events, we don't simply retrieve stored recordings, but actively reconstruct experiences from various memory fragments. We fill in details, make logical inferences, and create coherent narratives from incomplete information. Confabulation reveals the brain's powerful drive to create coherent, meaningful narratives from available information. Rather than acknowledging memory gaps or uncertainty, the brain often prefers to construct plausible explanations, even when these explanations are completely incorrect. The content of confabulations is not random, but follows predictable patterns. Confabulated memories often involve familiar people, places, and activities. They tend to be consistent with the person's beliefs, values, and typical experiences. This suggests that confabulation draws on existing knowledge structures and schemas. Social and cultural factors influence the content and likelihood of confabulation. Expectations about what should have happened, cultural scripts for typical events, and social pressure to provide coherent accounts can all contribute to confabulatory responses. Confabulation has important implications for understanding eyewitness testimony and memory-based evidence. Even honest, well-intentioned witnesses might provide confidently stated, but completely inaccurate information. The distinction between lying and confabulating is crucial for legal and clinical contexts. Treatment approaches for pathological confabulation focus on reality orientation, external memory aids, and strategies for acknowledging uncertainty rather than fabricating information. However, complete elimination of confabulatory tendencies is often difficult because they're rooted in fundamental memory processes. Seventh component, Mandela effect. The Mandela effect refers to instances where large groups of people share the same false memory about past events. Named after the widespread false memory that Nelson Mandela died in prison in the 1980s, when he actually died in 2013, this phenomenon demonstrates how collective false memories can emerge and persist. Common examples of the Mandela effect include remembering the Berenstain Bears instead of the Berenstain Bears, thinking that the Monopoly man wears a monocle when he doesn't, or recalling a movie called Shazam starring Sinbad that never existed. These shared false memories are often surprisingly specific and detailed. The Mandela effect reveals several important aspects of memory function. It demonstrates that memory errors aren't random but often follow predictable patterns based on expectations, associations, and logical inferences. Many Mandela effect examples involve memories that seem more logical or consistent than reality. Confabulation and reconstruction processes contribute to the Mandela effect. When people encounter gaps in their memory, they unconsciously fill in details that seem reasonable or expected. If multiple people make similar logical inferences, shared false memories can emerge. Social reinforcement plays a crucial role in maintaining Mandela effect memories. When people discover that others share their false memories, it increases confidence in the incorrect recollection. The social validation makes the false memory seem more credible than individual doubt about its accuracy. The internet has amplified the Mandela effect by making it easier for people with similar false memories to find each other and reinforce their incorrect recollections. Online communities dedicated to Mandela effect examples can strengthen false memories through repeated discussion and validation. Media exposure and cultural transmission contribute to many Mandela effect examples. Parodies, references, and misquotations in popular culture can become more familiar than the original sources, leading to false memories about what was actually said or shown in the original material. The power of suggestion influences Mandela effect formation. When someone proposes a false memory that seems plausible, it can implant that false memory in others who might not have had any clear recollection of the original event or information. Some proposed explanations for the Mandela effect range from the mundane to the fantastical. While some people attribute it to parallel universes or timeline changes, psychological explanations involving normal memory processes provide more scientifically supported accounts of the phenomenon. Understanding the Mandela effect has practical implications for recognizing the limitations of collective memory and the importance of verifying information from reliable sources rather than relying solely on shared recollections, no matter how confident or widespread they might be. Eighth component, method of loci. The method of loci, also known as the memory palace technique, is one of the oldest and most effective memory enhancement strategies. Dating back to ancient Greek and Roman times, this technique uses spatial memory and visualization to dramatically improve recall of sequential information. The technique works by associating items you want to remember with specific locations in a familiar environment, such as rooms in your house or landmarks along a familiar route. You mentally walk through this environment in a consistent order, placing memory items at each location, and later retracing your steps to recall the information. Ancient orators used the method of loci to memorize lengthy speeches without notes. They would mentally place different parts of their speech at various locations in familiar buildings, then mentally walk through the building during their presentation to recall each section in order. The effectiveness of the method of loci relies on several memory principles. Spatial memory is one of our strongest memory systems, evolved to help us navigate complex environments. Visual imagery engages multiple brain areas simultaneously, creating richer and more memorable associations than verbal repetition alone. The technique also benefits from the elaborative encoding principle. Instead of simply repeating information, you create meaningful associations between new information and existing knowledge. The more elaborate and distinctive these associations, the better the recall. Modern research has confirmed the remarkable effectiveness of the method of loci. Studies show that people using this technique can memorize and recall lists of hundreds of items with near-perfect accuracy. Memory champions in competitions routinely use variations of this ancient technique. The method can be adapted for different types of information. Historical dates might be placed along a familiar street, with each house representing a different event. Scientific processes might be distributed through rooms in your home, with each room containing a different step in the sequence. Creating effective memory palaces requires practice and creativity. The locations should be familiar and easily visualized. The route through the locations should be logical and consistent. The associations between information and locations should be vivid, unusual, or emotionally engaging to maximize memorability. The method of loci works particularly well for information that has a natural sequence or order. Shopping lists, presentation points, historical timelines, and procedural steps all lend themselves well to this technique. However, it's less suitable for abstract concepts or information without clear sequential structure. Training in the method of loci can provide lasting benefits for memory performance. Once people learn to use spatial visual associations effectively, they often apply these principles to other memory tasks, leading to general improvements in learning and recall abilities. Ninth component, memory interference. Memory interference occurs when similar memories compete with each other, making it difficult to recall specific information accurately. This phenomenon explains many everyday memory failures and reveals important principles about how memories are organized and retrieved in the brain. There are two main types of interference. Proactive interference happens when old learning interferes with new learning. If you've studied Spanish for years and then start learning Italian, your Spanish vocabulary might interfere with learning Italian words. Retroactive interference occurs when new learning interferes with recalling old information. Learning Italian might make it harder to recall Spanish words you knew perfectly before. Similarity is the key factor determining interference strength. The more similar two pieces of information are, the more likely they are to interfere with each other. This explains why students often confuse similar concepts, dates, or formulas when studying related subjects. Interference effects are particularly strong for paired associate learning, where you must learn specific connections between items. Learning that casa means house in Spanish might interfere with learning that casa means hunt in Italian. The shared cue word creates competition between the two associations. The fan effect demonstrates how increasing the number of associations to a single cue slows retrieval time. The more facts you know about a particular person or concept, the longer it takes to recall any specific fact about them. This occurs because all associated information competes for retrieval. Interference can be reduced through several strategies. Distributed practice, where learning sessions are spread over time, reduces interference compared to mass practice. Contextual variation, where similar information is learned in different environments or states, can help create distinctive memory traces that don't interfere with each other. Overlearning, where you continue practicing beyond the point of initial mastery, can make memories more resistant to interference. Well-learned information develops stronger memory traces that are less vulnerable to competition from similar memories. Sleep plays a crucial role in reducing interference. During sleep, the brain appears to reorganize memories, strengthening important information and reducing interference between similar memories. This is one reason why sleep is so important for learning and memory consolidation. Interference effects have practical implications for education and training. Subjects that contain similar concepts should be taught with attention to potential interference. Students should be warned about likely confusions and given strategies for keeping similar information distinct. Understanding interference helps explain why some learning strategies are more effective than others. Techniques that create distinctive, well-elaborated memories are less susceptible to interference than rote repetition of similar information. 10th component, memory consolidation. Memory consolidation is the process by which newly formed memories become stable and integrated into long-term storage. This process transforms fragile, easily disrupted memories into robust, enduring traces that can last a lifetime. Understanding consolidation reveals how experiences become permanent parts of our personal history. Consolidation occurs at multiple timescales. Synaptic consolidation happens within minutes to hours after learning, involving protein synthesis and structural changes at individual synapses. Systems consolidation occurs over weeks to years, involving the gradual transfer of memories from the hippocampus to cortical storage sites. The molecular mechanisms of consolidation involve complex cascades of gene expression and protein synthesis. Immediate early genes are activated within minutes of learning, triggering the production of proteins necessary for structural changes in neural connections. These changes must occur within a critical time window or memories will not be consolidated. Sleep plays a fundamental role in memory consolidation. During slow-wave sleep, the brain replays recent experiences, strengthening important memories and integrating them with existing knowledge. REM sleep appears to be particularly important for consolidating procedural and emotional memories. Memory consolidation is not a passive storage process, but involves active reorganization and integration. New memories are not simply filed away, but are connected to existing knowledge networks, often changing both the new memory and related old memories in the process. The reconsolidation process reveals that even well-established memories can become labeled again when retrieved. Each time we recall a memory, it enters a temporary state where it can be modified or even disrupted. This explains how memories can change over time through repeated recall. Emotional arousal significantly enhances memory consolidation. Stress hormones like cortisol and norepinephrine, released during emotional experiences, promote the consolidation of emotionally significant memories, while potentially impairing consolidation of neutral information learned around the same time. Interference can disrupt consolidation if it occurs too soon after learning. New learning can interfere with the consolidation of recently acquired information, which is why taking a break after studying or avoiding similar activities immediately after learning can improve retention. Various factors can enhance or impair consolidation. Exercise, moderate stress, and social interaction can promote consolidation, while alcohol, sleep deprivation, and chronic stress can impair it. Understanding these factors helps optimize learning and memory formation. The clinical implications of consolidation research are significant. Many memory disorders involve impaired consolidation processes. Therapeutic interventions that target consolidation mechanisms might help treat conditions like PTSD, where traumatic memories are over-consolidated, or Alzheimer's disease, where consolidation is impaired. Conclusion: the marvel and mystery of memory. Our journey through the landscape of memory and forgetting reveals both the remarkable capabilities and surprising limitations of human memory. We've seen how memory is not simply a biological recording device, but an active, creative system that constantly reconstructs our past while shaping our present and future. The complexity of memory systems, from the brief workspace of short-term memory to the vast networks of long-term storage, demonstrates the sophisticated evolution of human cognitive abilities. These systems work together seamlessly most of the time, allowing us to learn, remember, and build upon our experiences in ways that define our humanity. Yet memory's reconstructive nature also makes it fallible in ways that can be both troubling and fascinating. False memories feel as real as true ones. Shared false memories can emerge in groups, and our recollections change each time we access them. These limitations remind us to approach memory with both appreciation and humility. Understanding memory processes has profound practical implications. The forgetting curves show us why spaced repetition is more effective than cramming. Serial position effects guide us in structuring presentations and communications. The method of loci demonstrates the power of spatial visual associations for enhancing recall. The research on interference helps explain why some learning is difficult and suggests strategies for reducing confusion between similar concepts. Knowledge about consolidation reveals why sleep, exercise, and emotional state matter so much for learning and memory formation. Perhaps most importantly, understanding memory helps us develop realistic expectations about what we can and cannot remember. This knowledge can reduce frustration with normal forgetting while helping us develop more effective strategies for important learning and recall tasks. The study of memory also raises profound questions about the nature of personal identity and consciousness. If our memories are constantly being reconstructed and potentially altered, what does this mean for our sense of self? How do we maintain continuity of identity when our memories of the past are not fixed recordings, but dynamic reconstructions? Memory research continues to evolve with new technologies and methodologies. Brain imaging allows us to watch memory processes in action. Computational models help us understand the mechanisms underlying different memory phenomena. Clinical research provides insights into what happens when memory systems malfunction. As we learn more about memory, we also discover more about learning, thinking, and human nature itself. Memory is not just about the past, it's the foundation for all higher cognitive functions. Without memory, we couldn't recognize faces, understand language, solve problems, or plan for the future. The marvel of memory lies not in its perfection, but in its extraordinary ability to create meaning from experience. Despite its limitations and fallibilities, memory allows us to learn from the past, navigate the present, and imagine the future. It transforms isolated moments into coherent life stories and individual experiences into shared cultural knowledge. Thank you for joining me in exploring the fascinating world of memory and forgetting. Remember that your memory system, for all its quirks and limitations, is performing millions of remarkable operations every day. By understanding how it works, you can work with it more effectively, appreciating both its incredible capabilities and its very human limitations. Your memories make you who you are, not because they're perfect recordings of the past, but because they're meaningful reconstructions that connect your experiences into the ongoing story of your life. Embrace both the marvel and the mystery of this extraordinary system that makes human consciousness possible.